Thanks for the introduction and for the opportunity to speak. And this is joint work with Edward Bryden and Dimitri Kazaris. And we want to study the intrinsic flat stability of Llarull's theorem in dimension 3. So let me remind you of Llarull's theorem. Here we state it in two different ways. And so one way to think about it is that any change to a round sphere's Riemannian structure, which increases the scalar curvature, must decrease some distances. Or another way of saying it, you have a Riemannian n sphere, and the scalar curvature is at least n times n minus 1, and its distance function is bounded below by the unit spheres, then it has to be isometric to the unit sphere. And in fact, Llarull proved something a bit more general than this. I just state it in this way because this is the form in which we'll be able to prove stability, but there is a more general statement, and it uses spinors and the Dirac operator. And this has been extended to sort of less regular metrics and general dimensions. And so there's been this is more recent work on extending these things to general metrics like W1P metrics in particular. But that's in the rigidity case as well. And what we're interested in studying here is the stability of this rigidity statement. So just to give us more of like a vague question of what we mean by stability here, let's say you have a sequence of Riemannian manifolds defined on the 3 sphere, and you have this Lipschitz condition on the distance functions, comparing them in this way. And there can be various different ways you want to quantify what it means to be the almost rigidity statement. So in this case, you could say that the scalar curvature has to be bigger than or equal to 6 minus 1 over j, right? In this case, the dimension is 3, so n times n minus 1 is 6, and we're asking for a pointwise condition to be almost bigger than 6. You'll see later that we might modify this. There's various different ways of stating that. And you need some condition to rule out bubbling, and I'll show you a picture of what I mean by that. But a lot of these stability questions, which involve scalar curvature, we know that bubbling is a phenomenon that can occur, and so oftentimes we say that some condition needs to be imposed to rule out bubbling, and there's a few different choices. I'll talk about 2 of them in this talk in a few slides. And the question is then, under these conditions, does the sequence converge in the Riemannian-Wenger intrinsic flat sense to a round sphere, right, to the rigid object? This was mentioned by Gromov in the paper called the spherical stability problem. And explicit examples have been constructed by Paul Sweeney recently that show that lots of splines can happen and bubbles can happen and various other phenomena he shows explicitly. And in that same paper, a precise conjecture is given in all dimensions where the min A condition is opposed to rule out bubbling. I'll say a little bit about what the min A condition is later. Okay, but this is the basic question, and I'll make it more precise later when we get to the theorem. So what can happen? Well, first of all, in most of these scalar curvature stability problems, you can have splines appearing, right? So the same thing with the positive mass theorem, stability of the Groth conjecture, and in the case of the Llarull theorem, as soon as you allow the scalar curvature to dip a little bit below the rigid condition, you can get lots of these splines. And when you have increasingly many splines, there cannot be a Gromov-Hausdorff limit. This follows by Gromov's compactness theorem. So that's one reason why we are considering the intrinsic flat convergence. I just saw Christina's question. I think the conjecture is an all.
You may have written that, but I'm just saying 3D is all I ever conjecture.
There's a recent result that maybe. Well, anyway, so yeah.
Anyway, I won't.
Definitely in 3 dimensions, but and because of the Lipschitz condition, it's possibly a little bit more likely to extend in all dimensions without extra conditions. But in any case, I'm just going to talk about some case in this talk of the conjecture. So anyway, the first issue is lots of splines can happen. We're going to handle that by the topology that we use on the convergence of a sequence. And then the other issue is, the other issue that can happen is bubbling, or we call this other worlds forming. And the issue here is that you can have these thin necks, which have that satisfy the scalar curvature condition. This is something that Paul Sweeney showed is possible explicitly under these conditions on the sphere, but it's kind of been known in a lot of different situations where the scalar curvature rigidity problems become almost rigid. And what happens is behind that small neck, you lose the control that you have from the Lipschitz condition, right? Because the Lipschitz condition is controlling this bulk sphere part and giving you some control there. But behind the neck, the Lipschitz condition is very weak. It's going to take this entire other world and send it onto a small ball. And that somehow is not giving you the same control. And so behind that neck, you can have anything with anything with scalar curvature bigger than 6 can show up. And so the picture is not meant to be like exactly what could show up, but just it's more like to suggest that really wild things can happen behind those necks. It could actually be just other spheres of different sizes, or they could be more wild than that. And so we don't expect that part to be stable. And so we're going to remove that possibility by imposing some conditions. So this is what I was talking about earlier, in imposing a condition to get rid of bubbling. So there's various different choices, but the choice that we use that I will espouse here is to impose a Cheeger isoparametric constant. So just to remind you what that is here, it's a type of isoparametric constant where you take the area of some separating surface S and divide it by the minimum of the volume of the two regions that it separates your compact manifold into. And it's important here that the power of the area is 1 and the power of the volume in the denominator is 1, because in that case, splines can still form. Like you can have a uniformly bounded Cheeger constant and still have splines because of the difference in powers here. As soon as you impose a higher power in the denominator, which is like a more traditional isoparametric inequality, then you remove the possibility of splines. And we don't want to remove that possibility. So that's one of the reasons why we care about the Cheeger constant, or in this case, but it does remove the possibility of bubbling. So in this picture, you know, the surface on the neck, if that area becomes small, it's going to break it up into two bubbles. You know, one could be the bulk unit sphere, and the other one could just be another bubble. And that's not going to be allowed if you require the Cheeger constant to be bounded from below. And so what that means is if you impose a lower bound on the Cheeger constant, and you can find some surface who you know the area is going to 0, then you can deduce that the volume of the regions that splits the manifold into the minimum of those volumes must be going to 0. So that can be useful in combination. If you're familiar with the Cohn Dong and Antoine Song arguments, this kind of thing can be useful. The other thing that makes it really useful is, so you have this isoparametric representation, which is like the geometric representation, but then it's equivalent to this analytic representation that gives you a Sobolev inequality, right? So you can compare the L1 of the gradient divided by this sort of Poincare type constant F minus a constant K. And that K is not necessarily the average, but it is realized. So you can find the constant K. So this is why I like this particular assumption for getting rid of bubbling, because it has a natural geometric meaning, but it also has a very natural analytic meaning. And so we're able to go between the two of them when studying these problems. And since we're going to apply this to space-time harmonic functions, we really need some kind of analysis interpretation in order to use this assumption on the harmonic functions. And just to tell you what the Min A condition, because this shows up in a lot of similar scalar curvature problems, in that condition, you ask that the area of all closed minimal surfaces be bounded below by some constant A. That also gets rid of bubbling, and also gets rid of these tunneling phenomenon that shows up in other problems with scalar curvature stability. And just a question that I won't really say anything about is just, what is the relationship between this Cheeger constant and the Min A condition? This is a question that someone could think about. But in this talk, again, we're gonna use the Cheeger constant as our condition. And so let's look at the theorem. I thought I put pauses here. I guess not. Okay, let's look at the theorem. So first of all, we define the class that we're going to study, right? So you have a stability problem. You have to define the class of manifolds that you're going to consider. And so we have these Riemannian three spheres. They have to have the distance lower bound, which we state in terms of the metric, but because this is a global assumption, it's equivalent to the distance. And then you need a volume upper bound and a diameter of upper bound, and then the Cheeger constant lower bound. And just to say a little bit about the philosophy here, when you have these scalar curvature stability problems, there's going to be some conditions which are sort of forced upon you because of the rigidity assumption, right? So the distance lower bound and the scalar curvature becoming almost bigger than 6 are forced upon us because of the stability. The Cheeger constant is forced upon us because we want to get rid of bubbling. And these other two conditions I think of as like compactness conditions to make sure that the sequence does not like go off to infinity or become unruly for non-interesting reasons. So these are kind of compactness conditions here. Okay, so for this class of Riemannian manifolds, we're going to quantify the scalar curvature almost becoming larger than 6 in this sort of L2 way. So the 6 minus the scalar curvature to the plus is just looking at the positive part of that that term and asking that in L2 that thing goes to 0. So somehow this is a different way of quantifying that. It's natural for the space-time harmonic functions that I'll show you later. And under that assumption, we can show that they converge, and this fancy VF is standing for the volume Samani-Wenger intrinsic flat convergence of these manifolds. Now, interestingly enough, if you were paying attention to arXiv recently, there was a paper posted last Tuesday by Sven Hirsch and Yu Zhang, which proves stability in n dimensions using spinors. And so that's an interesting new development. And they use a similar class. They replace the Cheeger constant with the Poincare constant, which is slightly different. But they get a version of this theorem in all dimensions using spinors.
Brian, can you also take the lower bound on the areas? So not so that you don't compare the metrics, the Lipschitz bound, but you have a comparison between two-dimensional areas, like in Llarull's original theorem. Is this possible here?
Yeah, so we didn't try, though I am a little bit skeptical. I don't know. I think it would be difficult, maybe not possible. And
yeah,
even but I'm not sure because we didn't really try. But even in this spinner's case, they're not doing that except for they have a third result where they're able to do that, but in the style of this, like finding a bad set that you're going to remove and showing like CK convergence on the remainder. So,
okay.
But yeah, that's interesting because that's like the full generality of the original Llarull theorem. So, yeah, but we didn't think about it.
But for this Llarull theorem, either with diameter or with area, there are indeed several different proofs, right? So there is direct theoretic proof, and there is one proof of with Marcus and nerves for areas, which is geometrically look to me most attractive, which give you very kind of fair picture of what happens, right? It uses minimum surface of index 1. But this for area.
Whose proof is that?
It's a proof of Marcus and nerves. They show,
okay.
yeah. And they make some estimate for surfaces, and this is particularly implies Llarull kind of theorem with area. And it's very geometric, so it seems everything would happen there, how non-stability may break down. And also you can prove there is a similar argument with mu bubbles, but it proves slightly more. It proves this Llarull type theorem for double punctured sphere, but it uses the distances this time rather than areas, right? And so I wonder what exactly happens with stability for this argument. Just look at this, this perfect argument, know everything at every step, what happens, and at which point stability breaks down, right? We perfectly know exactly what happened in the proof. They're very kind of transparent geometric proofs, especially the second one. Marcos and nerves is slightly delicate if the topology is not spherical, right? There is some problem there if topology is not spherical, if it's a different topology, then you must be slightly more careful. But the second proof is very robust, very primitive. It depends on distances. It doesn't work with areas. And it seems must tell you everything about stability, what you can imagine. Of course, there may be something hidden, but it seems because when it's not a puncture, you can do it for every point. You have to take any point, take mu bubble, you know everything about any mu bubble. So it must be very, very kind of tricky to bypass it, yeah. Right, so that's, and then again the question, basic question which arises. So what you believe that you can cut off, you don't, whatever happens, you can cut off the small kind of grass which grows there with all those bubbles. This universe goes away, and there is a bulk of matter where everything is converges in all conceivable sense to this and the sphere, right? Right. This is naive conjecture that you can cut away something very thin, make very thin cuts, and then everything else will be kind of almost isometric, not just any kind of tricky sense, but really almost isometric by Lipschitz, equivalent to the sphere, right? This kind of naively what you believe. There is no counterexamples of that, right? Right, that you can cut away something, and the cut have small lengths, right? There's small areas. Small areas, and then contain negligible amount of volume, and so they don't affect the distance because they're so thin. This cut is having small areas, so it doesn't change geometry outside, and the geometry converges just by Lipschitz to the Euclidean, to the spherical geometry. No? So you can say it in other terms that there are sequences of open set inside where distance geometry just converges to spherical geometry. That would be naive formulation, right? That is open dense subset of the more and more dense, bigger and bigger sets where geometry converges distance-wise. No, or it's other counter example. This is what my question. It's naively what you expect because all bubbles are very touch very little the sphere, yeah. Little, very, very thin necks. And Penrose inequality says, as was Christina explained to me, they cannot cover much ground. Yeah. So, but I want even accounting it's completely naive idea what I say. And I'm curious exactly. The second proof is mu bubble looks to me most robust. It's all in all arguments here is the most robust proof, but it's for distance. It's not for areas, of course. This area is very delicate. This area is become so flabby, right? So much harder to prove something with this area as far as stability goes.
Right.
It's good points.
Yeah, thanks for the discussion. I can tell you where the distance comes up a little bit later on when I get into the proof. But yeah, it's it allows us to compare the space-time harmonic functions to the background sphere in an important way. Okay, so this is the theorem that we have, and so again, there's this issue of worrying about these bubbling and the splines that I showed you earlier. We get rid of the bubbling via the Cheeger constant, and then the splines are taken care of by intrinsic flat convergence. And so I won't define intrinsic flat convergence carefully, but I want to just talk about the intuition, and then I want to show you an important tool by myself and Christina Somani and Raquel Paralysis that allows us to estimate intrinsic flat convergence. And so, this is kind of a depiction of Illman's example. You have this red round sphere in the back, and then you have this manifold that's developing more and more splines, but the splines have small volume, and they satisfy this Lipschitz condition. You can do that explicitly. They have no Gromov-Hausdorff limit, but they will have an intrinsic flat limit. This was introduced by Christina Sormani and Stefan Wenger in 2010. And the intuition here is that, you don't need to control distances everywhere. They can be sort of unchecked as long as that occurs on sets of small measure, right? So splines and things like that, small volume. So splines are the kinds of things that this can handle really well, as well as like kind of generalized splines and things like that in higher dimensions of small volume. And if you look at the careful definition, it follows something similar to Gromov-Hausdorff convergence. You're going to have some Riemannian metric M1 and some other Riemannian metric M0. That's like the blue and the red spaces here in the picture, and you're going to isometrically embed them into some larger, in this case, a complete metric space Z. And instead of measuring their Hausdorff distance in the metric space Z, you're going to measure what's called their flat distance of Federer and Fleming that was extended to metric spaces by Ambrosio and Kirchheim. And roughly speaking, it measures like this filling volume between them. And depending on how you construct this metric space Z, you can do it cleverly so that you can get estimates. And in particular, one quantitative estimate that we have that we use to prove a lot of different stability theorems involving scalar curvature that have been proved, and we also use for the proof of the Llarull theorem, is the following. So you have I think this J is supposed to be well, let's see. So you have a Riemannian manifold MJ, and you have another background Riemannian manifold G0, and you want to estimate the intrinsic flat convergence between those. So you need a bound on the diameter, and you need a bound on the volume, but these are somehow just bounds. And then you're going to require this Lipschitz condition between the distances. And here's the big part where you get the intuition from intrinsic flat convergence. So WJ is the good set. So here you can think about this kind of actually related to what Gromov was just talking about. This is the set where you don't expect splines and bubbles or anything like that. So there's this good set that you can identify, WJ. And on that good set, you can estimate distances in this very strong way, right? So you can estimate distances from above as well on an order of 2 delta J. So you're kind of asking for uniform convergence on WJ. And the trick is you need to make sure that that WJ is almost the entire volume of the manifold. And if you can do that, then you get the following quantitative estimate, right? So the flat distance between these two, the background Riemannian manifold M0 and the sequence can be made less than or equal to 2 times the volume bound, which you're hoping goes to 0, plus this Hj times V. And the point is that this Hj will go to 0 as long as you can estimate delta J. Now, generally, so this does give you a quantitative estimate, but generally speaking, it's not hard to get a quantitative estimate of Vj along a sequence, but generally it's not easy to make this Hj quantitative. So you'll see that in practice, we're going to use this in a sequential stability sort of way, and that I'll state here in a second. But if you could come up with a way of doing this in a quantitative way, then you would get a quantitative estimate of intrinsic flat convergence. And again, the picture here is that the yellow set is the bad set where you're not going to control distances, and this kind of blue set is where is the WJ where you have control. And similarly here, anywhere where you see splines is sort of a part of the complement of WJ. And so the way that we use that quantitative estimate to get a theorem that allows us to give some natural geometric hypotheses which conclude intrinsic flat convergence is the following. So we're going to be on a compact, connected, oriented, and smooth Riemannian manifold without boundary, though there are versions of this theorem with boundary. We just won't need them for this talk. And we're going to impose this distance from below condition. In general, you can loosen it up a little bit for this theorem, and you just need this 1 minus C over J, where that C over J is a sequence that converges to 0. And so we call that convergence from below, or distance bounded from below. You need a bound on diameter, and you need to assume volume convergence. So under these conditions, we give this tool which allows you to conclude volume preserving intrinsic flat convergence. And, we call this theorem the volume above distance below theorem, or VADB for short. That's been the kind of name that we've attached to this. And I think about this as a type of squeeze theorem, right? So you think of the volume as being squeezed against the distance below condition. And when you squeeze those things together, you get this volume preserving intrinsic flat convergence. But the other sort of philosophy behind this theorem was to provide a tool to the geometric analysis community for those who maybe haven't taken the time to understand all the details of intrinsic flat convergence. In some sense, you don't have to now, because as long as you can apply these estimates, then you can conclude volume preserving intrinsic flat convergence, right? So then this tool gives you a way of doing that by just understanding these geometric hypotheses. So let me give you. By the way, before I move on, this theorem though should sort of hold in more general settings. So, for instance, you shouldn't need the sequence to have the same topology, but that does make it harder. You should be able to handle boundary, and possibly you should maybe be able to handle sort of less regular types of metrics. Here we're allowed, the background metric has to be smooth, and the sequence is allowed to be continuous, but perhaps this holds on even more general assumptions. So there's some interest in extending this to lots of different cases. Let me just give you some idea of how the proof goes. I won't spend too much time here, but in an earlier paper by Christina and myself, we proved the following. So this is like an earlier type of squeeze theorem, which is not quite as strong as the VADB theorem. So you're in the same setting. You have a sequence of compact connected continuous Riemann manifolds. You have a background smooth Riemann manifold. You assume this Lipschitz condition, and you have volume convergence. Then the theorem says that there has to exist a subsequence so that the distance functions converge pointwise almost everywhere for almost every PQ and M cross M. Okay, so this is where this proof really involves the squeeze theorem part of the intuition, is to get this pointwise almost everywhere convergence of distances. And let me just try to give you a rough idea. I'm not going to explain the entire proof, but the point is that what you're going to try to do is so you know that the background metric G0 we assume is smooth. And so we're going to use like facts from differential geometry about foliating via distance realizing curves and things. So first of all, P and Q are not going to be cut points of each other. And so you can pick a blue length minimizing geodesic between them, and then you're going to pick some hypersurface in red that bends enough so that when you look at foliating this region by geodesics, the foliation remains non-trivial. Like the geodesics don't bump into each other. And you can do that, and you control all that because you know G0 is smooth. It's just like a smooth background Riemann manifold. So you foliate a region of full volume with distance realizing geodesics with respect to G0. And then, again, I'm only going to give you the rough idea, so there's lots of details missing here. But the point is, if you look at the difference of the distance functions, remember, you're comparing them from one direction. So you already have an estimate on this from one direction. So you need to compare it from the other direction, which is the one we're comparing here. And if you think about the distance with respect to Gj, it's always smaller than the length of these curves. That's just how the distance function is defined. And because the distance here with respect to G0 and the foliation is literally the length of the curves, you can replace it in this inequality the following way. And then there's many co-area steps missing that eventually can get you from integrating over this n-1 dimensional hypersurface, which is in red, the lengths, to the volume of this region with respect to Gj and the volume with respect to G0. And that's where the squeeze theorem kind of thing is happening, where if the volume is converting to 0 and you have a comparison between these distance functions, then they must be going to 0 in some integral sense, where we eventually integrate this over more pieces that I'm not showing you. And because you have an integral of the distance functions going to 0, which is positive, that's why you get pointwise almost everywhere convergence of the distance functions. And so this is the place where we use the background metric is smooth, but if you could produce a foliation by distance realizing geodesics on some special length space, that would also possibly work, though maybe something else would throw throw a bone in the project. I'm not sure, but I think something like that could also work. And so now you have pointwise almost everywhere convergence of distances on M cross M. So then you can apply Egroff's theorem to show that there's a set of small measure, so that when you're outside that set of small measure, you have uniform convergence of the distance function. Okay, and so that's how you're going to finish the proof. You're going to apply the quantitative estimate of the intrinsic flat convergence using Egroff's theorem, because now you have a good set where you have uniform convergence of the distance function, and you have a bad set which has to have small volume. So that's the rough idea. There's many details to fill in, but that gives you the idea. And so when we prove Llarull stability, we're going to apply the VADB theorem, right? So let me just go back to it for a second. So that means we're going to assume this right away in that stronger form, the Lipschitz condition. And we assume a diameter bound. By the way, that's the only reason why we have to assume a diameter bound is to apply this VADB theorem. So we assume that in the Llarull stability for that. And so if we want to apply this theorem, we need volume convergence. So that's our goal when we talk about space-time harmonic functions here. Our goal is to show volume convergence, and then we can apply this theorem and we get the volume preserving intrinsic flat convergence. And this is the same, this technique is what Sven Hirsch and Yu Zhang also use this approach. So both approaches use the VADB theorem. Okay, but let me move on from the VADB theorem. That's the big tool that we're going to use. But the other big tool that we're going to use is the one that Marcus talked about in a more general setting, which is space-time harmonic functions. But because we're only going to study this in the setting of Llarull potentials, we give it this kind of sexier name of Llarull potentials. So that's what we call it. The Llarull potential is specifically a space-time harmonic function on the sphere. Here, theta is going to always represent distances on the round sphere from some pole P. And then the PDE is going to be a solution to, from S3 to the real numbers, a solution to this boundary value problem. And notice that cotangent becomes singular at P and minus P. We have certain boundary conditions there. And so first of all, by the maximum principle, you note that the Llarull potential has to stay between -1 and +1. That's useful. And also, you should just note that on the round sphere, the solution is just cosine of theta. And so the gradient is sine of theta, and that will be important later. And by the way, just so the technical place where we use this distance below condition in the proof is often you're going to have gradients of theta showing up in various different formulas. And sometimes you're going to measure that gradient with respect to G, and sometimes you're going to measure that gradient with respect to the round sphere. And in order to compare the gradient of theta with respect to G and the gradient of theta with respect to the round sphere, which we know is 1, that's a lot of times where the assumption of the distance below is going to be used in the technical part of the proof. Okay, and so with these Llarull potentials, they're able to give another proof of Llarull's theorem. Again, it uses the distance condition, not the area condition. And but they're allowed to consider a manifold which is not necessarily a sphere. But so then they have to impose this homology condition for the reasons that Marcus was talking about. But you have this Lipschitz map from this general Riemannian manifold to the sphere, and it has to be Lipschitz less than or equal to 1. And you get this nice formula that relates, on the one hand, almost being larger than 6 in the scalar curvature, on the other hand, a type of Hessian term, which is a little bit more complicated than what happened in the space-time harmonic case. And, sorry, in the positive mass theorem case. And so, but if scalar curvature is bigger than or equal to 6, then that's going to force this right-hand side to be 0. And again, if you study what it means for this Hessian term to be 0, there's a few deductions from there. You can see that that'll force L to be an isometry. And so they were able to prove a version of Llarull's theorem stated here. And what we're going to need actually, and they already knew about this, but they didn't need it. But by carefully reworking the calculation in 16, you can see that actually there's other terms that go to 0. It's not just this Hessian term. So we'll see that there are going to be some other terms which also go to 0, which are going to be useful for us. Okay, so again, the two tools, or the three tools, if you want, if I want to break it up into three, is going to be the VADV theorem, the Llarull potentials, and this this inequality that relates the scalar curvature and the Hessian, a type of Hessian term of the Llarull potential. Okay, but remember again, our goal is to find convergence of volume. If we can find convergence of volume of a sequence, then that's enough to apply the VADV theorem. Okay, now this estimate is not something worth spending a lot of time on, but we can show that for any metric in our class and Llarull potential, we can get this sort of L2 gradient estimate. The only reason why I mention this is because I want you to think for a second about the difference between studying Llarull potentials in the presence of a Ricci curvature lower bound and the difference when you don't have that, right? So for instance, you should not expect anything like a Chen-Yao gradient estimate. And so you really shouldn't expect pointwise bounds on the gradient. And it's not necessarily true that you should expect any kind of Sobolev space kind of estimates either. And so we're able to get just by a simple PDE argument that anyone who's used to PDEs would try on this kind of equation, you can get this kind of an estimate. But we struggle to get like the typical PDE estimates any higher than this. I think we can do a little bit better in LP, but it's hard to get estimates much better than this without a Ricci curvature lower bound. And so a big part of the goal in the proof is to sort of lower our expectations and come up with new estimates that are somehow much weaker than what you typically would do for PDEs, but strong enough to get volume convergence. That's what I'm going to outline for you in the proof. It took a while to figure that out, that delicate game out. And so, so I showed you this formula that that follows from the Llarull potential work, and we're able to rewrite this in a slightly different way. So you can rewrite it as a gradient of this function. It's not an equality. You actually, when you do that, you introduce an inequality, but whatever, it's controlled in this following way. And this is important because we want to apply the Cheeger constant assumption, and we want to use the Poincare version of the Cheeger constant assumption. So we need it to re-look like a gradient of something, not just some complicated Hessian, right? So, okay, I just want you to note that that's what it looks like. And so, again, here's the statement of our theorem. So that's showing you where this Cheeger constant lower bound is going to be used, is to basically apply to that gradient term that's bounded by the scalar curvature quantity. That also explains why this is the scalar curvature quantity that we're looking at, because it basically it shows up in the formula, and after you do a Holder inequality to get rid of the gradient term of U. Okay, so let me just start with an outline of the proof, and then I'm going to go into slightly more details. So using the Cheeger constant bound, you can show that there's this positive constant, non-negative constant A, so that the following is true. So here we're using we use the Cheeger constant bound to get a Poincare inequality, and then that's where the A is coming from, like an integration constant. And then you use Chebyshev's inequality to show that where this term is bigger than tau, which is somehow the bad set, is controlled in the following way. And well, that motivates the definition of a good set, which is somehow the opposite of that. So where this term is less or equal to tau. And here we're taking some guidance from the papers by Kong Han Dong and then with Kong Han Dong and Antoine Song, where they look at asymptotic linear harmonic functions and define these good sets. But we go in quite a different direction here, because we only need one good set. We don't need to consider three somehow mutually orthogonal, almost orthogonal good sets. We're just going to need one of them, and we just need to show volume convergence. So we do take some ideas from them, but taken in a different direction. But here's the good set that we define. And so if you pick your parameter tau so that this thing goes to 0, that's not such a big deal. Then you can see that the volume of this good set is going to converge to the volume of the round sphere. But there we're taking volume with respect to the round sphere. So that's not what we need to apply the VADV theorem, but somehow it's filling up the entire sort of background manifold. Okay. But we need more than that. We want the volume with respect to GI of the good set to converge to the volume of the round sphere. So that's our goal. All right. Well, so in order to do that, the main estimate, which I'll show you some details about, is going to be to estimate this constant A of G. And let me try to give you some intuition about why you want to estimate it from this direction. So just take this term up here and think about it as being true everywhere, which it's not. Like, let's say this is always equal to 0. Then you're saying that the gradient of u is like a times sine of theta. Okay. If a is less than or equal to 1, so then you're saying the gradient of u is like a times sine of theta, where a is less than or equal to 1. But your u is supposed to go from 1 to -1 when you go from the North Pole to the South Pole. So in order for that to make sense everywhere, the distances on your manifold must be bigger than the round sphere. So you have some way to go from the North Pole to the South Pole with this small gradient, just intuitively speaking. So, but that's already, you're already assuming that. You're already assuming that your manifold is bigger than the round sphere. So that's not really the direction you want to estimate. Instead, you want to show that the A has to be becoming almost bigger than 1. Because then in some intuitive sense, you're saying that the distances have to be becoming smaller than the round sphere or equal to the round sphere. Not everywhere necessarily, but there has to be like some paths which you can take from the North Pole to the South Pole that have that condition. That's at least the idea. So that's why I'm gonna show you how to estimate this thing from below in this following sense. And that's why that's the right estimate to do, to look for. And then let me not say much about this now, but basically this is the other term which goes to 0. If you take 8 pi and subtract to the other side, that thing will go to 0 from this result on space-time harmonic functions in the previous work. And we'll use that to show that the volume 2 converges 0 and apply the VADB theorem. Okay, so that's the outline of the proof. Now I'm going to go into slightly more detail and mostly to show these last 2 steps, to show how you estimate A and how to use that to get the volume convergence. Okay, first, I don't want to spend too much time here, but this is the one place that we use the volume bound. And so we use the volume bound to say that you can pick antipodal points and look at the balls with respect to the round sphere around those points. And you can always pick 2 antipodal points where you can estimate the volume in this sort of quantifiable way. Basically, this is like a packing argument. If you couldn't do this, then you would contradict the volume bound. You pack the sphere with a bunch of these balls, and if you can't do this, then you somehow would violate the volume condition. So anyway, not a big deal, but this is the one place we use the volume condition to pick particular poles here. So that'll come up at the very end of the proof. Interestingly enough, though, the proof given by Sven and Zhang, they don't need a volume bound. So somehow we can think about what the difference is there. Okay, so again, we use this Cheever constant and Llarull potential to get, I've showed you this already, but now I'm showing you slightly more detail. So you apply the Poincare version of the Cheever constant to get this thing to be controlled. And then Chebyshev's inequality tells you that this set is controlled in the following way. And then similarly, you can rewrite this term here as a gradient of a function. It's not like obvious by looking at it, but it's not so surprising that you can do that. And if you do that and use the Cheever constant Poincare inequality again, you get a second integration constant and you get control of this term like this. And by Chebyshev's inequality, you can do a similar argument about the sort of the bad region where you're bigger than tau. So we get a second integration constant, which will be used a little bit. And so we're going to again define this good set where we have this kind of comparison to the gradient of u. And remember, sine of theta is like the gradient of the Llarull potential on the round sphere. So we're comparing the gradient of our Llarull potential with the gradient of the round sphere's potential. And because all these PDEs and inequalities will become unbounded or singular near P and negative P, we're going to remove two balls of radius T from the poles. And in order, so our new good set will be the same good set as before, but we remove sets around the poles. And that will come up again later on. Okay. So let me give you a flavor of the kinds of things that we can control now. So again, you have a little potential that's in the class that we're interested in studying. You have the centered at plus and minus P, and you have, you're smaller than the radius here, which is kind of technical. And you can get this kind of bound. Okay. And why is this interesting? Well, remember that on the round sphere, if you integrate cosecant cubed, that's not integrable. And so, and also, we know that the volumes between the round sphere and the metric G are comparable in this way. So this also should not be integrable, but you have this gradient term. So that means that this is like a very weak way of saying that the gradient has to go to 0 near the pole. Yeah, it's very weak, right? Because it doesn't have to go to 0 everywhere or anything like that, but it must be going to 0 in some sense in order to make this integral integrable, right? So this is the kind of thing that I was telling you before, that we're kind of right at the boundary of the kind of estimates you can get without Ritchie curvature bounds, but this is the kind of thing that we can get and is useful to us. Okay. So from there, we want something, we don't want to say better than that. We want to say what that means, right? So what we're really worried about, to give you the idea, is that you know the function's 1 at the pole, but you don't know how quickly it can move away from 1. And that's what we're worried about. We want to know that near the pole, you have to be close to 1. That's what we want. So we're going to try to use this estimate to say something like that. And if your gradient is close to 0 or going to 0, at least you might hope that, like in some average sense, that you have to be close to 1 that you can quantify. And so that's what we're able to do. We're able to show that we can't show it's close to 1 in a ball or anything strong like that. You would need Ritchie curvature. But you can say that in the sort of average integral sense, it has to be close to 1 near the pole P and -1 near the pole negative P in this quantified way coming from sine of T. Okay, so that's what we can glean from that previous inequality involving cosecant cubed and the gradient of U. And I don't know how much this helps right now. So let me just keep it intuitively and not talk about equation 27, but yeah, anyway, you can come back and ask me about that if you want, but I think the intuition is more interesting. But we still need a little bit more control than this. So this is helpful, but we want to know, basically want to know that there's at least 1 point near the pole which is close to 1. So we're going to try to use this to say that. And so we can quantify that in the following way. So this round sphere ball is going to ensure that we're close to the pole in some quantified way with respect to r. And gamma you should think of as being something close to 1. So here we're saying if you're close to the pole and you're not close to 1, then we can estimate the volume of that set in some quantified way. And similarly on the opposite pole, if you're close with respect to the round sphere to the negative P and you're not close to -1, then we can quantify the volume of that set. It can't be all of the round sphere ball, basically. And that's important. So we're going to use that to get this estimate on A of G. And again, although we don't do this using like the fundamental theorem of calculus argument, it's still that same kind of idea where you want to connect the pole P to pole minus P, knowing something about the gradient. And if you connect along some curve, that should connect up distances with the gradient and the fundamental theorem of calculus to give you an estimate on the size of the gradient. And I'll show you more specifically how we do that. But, okay. So you define this tilde good set, which is coming from the second use of the Cheeger constant to get these two integration variables, right? And we can choose these parameters carefully that come from the various estimates I showed you. Choose gamma to be close to 1, then you can show that there has to be a point that's in this good set where U is bigger than gamma. So that's saying U is close to 1, and U is close to the pole with respect to the round sphere. So you get to use all three of those. There's at least 1 point, and there's at least 1 point on the opposite pole. Okay, so this is what I'm talking about. We have to really give up our expectation for strong estimates, and instead, this is what we get. We're allowed to say that there's 1 point near the pole, which is close to 1, that is, it has this estimate, and similarly next to the minus pole. And if you have just 1 point in each of those sets, call it x plus and x minus, then you can just use the fact that they're in these good sets and plug it in and take the value of this at x plus and subtract the value at x minus. Because they're both less than or equal to tau in absolute value, you get this comparison to 2 tau. When you subtract here, notice the integration constants go away, so you don't need to estimate them ever. And here, these can be estimated by 2 gamma because of the fact that they're in these sets. And then lastly, you get A times the difference in cosine with respect to the round sphere's distances. And so you can estimate that by 2. And so you get this very simple estimate here, and that's how we get the estimate of A. Which is very important because, again, that gives us this strong understanding of this constant which compares the gradient of our Llarull potential to the gradient of the Llarull potential with respect to the round sphere. And these powers are not not so important, but we're all careful and explicit about that in the paper. Okay, so let me finish up the proof now. Again, here's our good set, and we remove balls around the P and minus P to get this other good set, and we want to estimate volumes. So here we use this this bound or this estimate on A now to allow us to estimate the volume between the good set with respect to G and the good set with respect to the round sphere to be small in this quantified sense. And I think, oh yeah, so I give us an idea. So let me try to give you an idea of how this gets used. Okay, so over here, this is a term. This is a term that can be shown to be small from the previous results by Marcus Curry and Sven and Dimitri and you, Yuzan. And so we're going to take that, and by using the estimate on A, you can show that you can replace this term by something like morally like 1, right? That's where the tilde is coming in. There's actually terms that are going to 0 when you do this, but I'm going to remove them for this argument. I'm just showing you the ideas. So you can estimate this using the estimate on A to transfer it into this term. Now, notice that because of the comparison between the volume forms, I can also compare this from below with respect to the same term integrated on the round sphere. But now on the round sphere, you can actually explicitly calculate what that would be. And if you integrate cosecant theta over the round sphere, you get 8 pi. And so that's going to squeeze, on one side, you're going to 8 pi, on one other side, you're going to 8 pi plus something more. And that's going to squeeze the volume forms to be identically equal to each other, or in the limit. That's going to give you the estimate on these volume forms. Okay, and finishing up the proof, then we're going to again equip each the Riemannian 3 sphere with Llarull potential centered at poles, so that we have volume control on the poles, like I showed you earlier. And there's some choices for these parameters, which we can give very explicitly. And here I want to first just take the round sphere, measure with respect to GI, and subtract the complement of the good set. Of course, that's just going to give you this good set. And we just showed that if you measure the volume with respect to GI, you can replace that with the volume with respect to the round sphere, plus a little extra, and then replace that with the volume of the round sphere here. That means if I want this term to converge to that one, I need to estimate this complement. And so here's where we choose the poles to have the volume estimates that I showed you earlier. So you can see that when you take the complement of this good set, it's at worst going to be the entire complement of the good set plus the entire round sphere ball around P and the entire round sphere around negative P. All three of these things can be estimated, as I've showed you, by terms going to 0. And so putting everything together, you see that the volume of this three-sphere respect to GI is squeezed in the following way. And if you apply then the VAB theorem, you get intrinsic flat convergence. And again, I just want to mention that Sven Hirsch and Yu Zhang also apply the VADB theorem and get a volume estimate. But the way that they get the estimate on volume is quite different. They have a good set, bad set type of argument, but they do not use these Llarull potentials. They use the original kind of spinner and Dirac formula rule. Okay, that's the end of my talk.